This is Kevin Ega with Math 250, Calculus 3, Lecture 7. So today we are going to cover several different things, just kind of mopping up the last bits of 13.5. First of all, we're going to talk about the relationship between three-dimensional conservative vector fields and curl. Okay, so we've mostly been talking about two-dimensional conservative vector fields, and we're going to tie in three-dimensional ones today. The next thing we're going to do is we're going to make kind of second derivatives. We're going to put div, grad, and curl together in various ways and see what you get. And the last thing is we want to see a few other ways of seeing Green's theorem. So those are the topics for today. So let's get started. Conservative vector fields. Recall in 2 dimensions I had this chart here. These are all the different ways to say that f is conservative here. Various things are independent of path or 0. And if the f is conservative, then we have Clairaut's condition q sub x equals p sub y. Now, of course, there was some kind of difficulty in talking about whether this implies that f is conservative, and we discussed that the other day. The similar story is going to also apply in 3 dimensions. Okay, so I didn't emphasize that this was all 2-dimensional, but of course at this point you can realize that, okay, this has got to be 2-dimensional, because 3 dimensions this would be p, q, and r. There would be 3 components, and there would be more versions of this. So in 3 dimensions, this is what it looks like. Okay, this will have p, q, and r. Okay, and I'm explicitly writing it out like this. The same thing as what I had before, and this is what we get for Clairaut's result. So remember, this is partial derivative with respect to x, y, and z. So there's actually 3 different mixed partials that we can talk about, and that corresponds to these three possibilities here. Qx, the partial derivative with respect to x, subderivative the partial derivative of this with respect to y. That's basically saying g sub xy should be equal to g sub yx. But you also have these guys with r and p. So partial derivative of p with respect to z should be the partial derivative of r with respect to x. That's because this is supposed to be gx, this is supposed to be gz. So this would be gzx, and this would be gxz. Those would be equal. And let's say same with this with y and z like that. Okay, so this is what Clairaut's theorem would say for a 3-dimensional vector field. Sorry, yeah, three-dimensional gradient of a function. These things don't change very much. I mean, of course, there's more. There's an rdz here, an rdz here. But other than that, the fact that this implies this, that's by the fundamental theorem of calculus for line integrals, same as before. This implies this for the same sorts of reasons. You basically define g to be the line integral from, say, the origin to where you are, plus a constant of f dot dr. The relationship between this and this is exactly the same proof. There's no difference at all. So all of these are still equivalent in 3 dimensions. The only thing that's now changed about this picture is, of course, these formulas that get a little bit, bigger with the z components. But also Clairaut's result here is a little more complicated. It's got 3 different components. So there we go. Let me take this and put it on one screen like this. Okay, so if this is the gradient of the function, then these things should be true. The funny thing about these things is if you look at the formula for curl, this is the formula for curl. These things here are the same thing as these that appear in this formula here. And what's funny is if qz is equal to r sub y, then r sub y minus q sub z is equal to 0. And p sub z minus r sub x would be 0 if this is equal to this. And if this is equal to this, then this would be 0. In other words, Clairaut's result can be stated as curl of this is equal to 0, 0, 0, it being the 0 vector. Okay, the curl of f is the 0 vector. So I think that's kind of cool that curl comes up exactly to summarize these 3 conditions. Can be summarized just as curl of f is equal to 0. We're going to come back to that at a later time. There is a version of Green's theorem that that applies in 3 dimensions, but we're going to talk about that later. It's called Stokes' theorem. That's in a later chapter. But first of all, I just want to appreciate that if you take a function and take the gradient of it, and then take the curl of it, you should get 0. Okay. Oh yeah, here it is. The three-dimensional version can now be stated with this curl being 0 as down here. Yeah, and this being implying this is going to require the three-dimensional version of Green's theorem called Stokes' theorem. Okay, what we see though, the important thing is that curl of the gradient of a function is 0. Actually, I can prove this directly. I guess I proved it just a little while ago, but just to sort of see it when this is the only thing we're focusing on. Let's say you have a function g, the gradient of g, and take the curl of it. So the gradient of g, it looks like this. Okay, partial derivative of g with respect to x, y, and z, put it into a vector like this. Of course, this is three-dimensional, otherwise I wouldn't be doing curl here. So it's got 3 components. And curl of this, okay, take the partial derivative of, well, you got to find partial derivative of this with respect to y, partial derivative of this with respect to z, and put it in this one, subtract. And you see gzy minus gyz, and so on. All of these things. And you see this is equal to 0 if for Clairaut's result to be true, this should equal to this. Right? So that should be 0. This should be equal to that, so that should be 0. This should be equal to that, that should be 0. So the curl of the gradient of a function is the 0 vector. Actually, there's another result that's kind of similar to this. The div of the curl is equal to 0. So here we go. Curl of PQ at R is given by this formula. And if I need to take the div of it, I'm going to take the partial derivative of this with respect to x, partial derivative of this with respect to y, partial derivative of this with respect to z, and add it up. Okay. And this is just the derivative of the difference is the difference of the derivatives. So this is r sub y is x. This is minus q sub zx, and so on. Just do the whole thing out like that. And then you see ryx and rxy are here. And by Clairaut, these are equals, and so the fact that one has a plus sign and one has a minus sign means they both cancel. And here's qzx, qxz, again these cancel, pzy, pyz, those cancel, and you get 0. So the div of the curl is equal to 0. All right, what else can we get when you put these different kinds of derivatives together, div, grad, and curl? So I've got a diagram here. These are scalar fields. These are vector fields. The gradient takes a scalar field and gives you a vector field. The div of a vector field is a scalar field. The curl of a vector field is a vector field. Okay, and if you piece these together, you get curl of gradient of g. So I can go gradient of this and then curl. And this one is, if I start here and do curl and then div, I get 0. Here's other possibilities. Div of grad. So I can start here, take grad and div, and you end up with this. Or I can start with a vector field, go div, then grad, I get this. Or I can start with a vector field, go curl, and then curl again, you get this. If you work it through, you can see that these are the only possibilities. I mean, I can't take grad of grad because the gradient of a scalar is a vector field, and I can't take the gradient of a vector field. So that doesn't work. If you work it out, you'll see that these are the only possibilities. And these two we know are 0. What about these guys? Okay. So this one, let's talk about that one first. Div of grad. Okay. So here's g, okay, and take the gradient of g, again, partial derivative with respect to x, y, and z here, and put it in the vector. Div of this means you take this part and take the partial derivative with respect to x, this, take the partial derivative with respect to y, this, take the partial derivative with respect to z, and add it up. And you get gxx plus gyy plus gzz. Okay. This is something that's pretty famous. It's called the Laplacian. Sometimes I call it the scalar Laplacian. I often don't use the word scalar if it's not said, then scalar is assumed. And it has this symbol here, this del squared g. If you think of it as using the mathematical pun, this del, and you take the magnitude squared, okay, then basically we're talking about this. So that's equal to this. I've written it this way as well, just to kind of get a different view on things. It's exactly the same thing as this one, of course, but you sometimes see this, sometimes this. This is a little bit more common. The Laplacian is really famous because it shows up in a lot of applications. Okay. By the way, this of the compositions, this is the one. This is one of those that can also work in 2 dimensions. So I've done everything in 3 dimensions here. If it's 2 dimensions, then of course you don't get this third component, and then this thing isn't here either. Um, and so that would be the 2-dimensional scalar Laplacian. Just get these two and not this one. Okay. And there are different versions of the wave equation depending on what kind of waves you're talking about. And for instance, sound waves would follow this equation. Water waves would be the 2-dimensional version. So u would be the height as a function of x and y, the plane. And basically, this is force equals mass times acceleration. This is how quickly the top of the water is going to move. Okay, at least the acceleration of the of that water is going to be related by this constant. It's going to be a positive constant times the scalar Laplacian in 2 dimensions. And so this is going to basically tell us the forces that are applied to that to that water. Wave equation can also be used, by the way, not only for water, but other things like the surface of a drum. If you want to see how it vibrates and all the different kinds of pitches you can get, you would study this and so on. You can do it in 1 dimension and have a string or a guitar string that's being plucked, right? Okay. The other one I have on the screen here is the Schrödinger equation. This is a famous equation from quantum mechanics, and it describes, say, how an electron or some kind of particle like that behaves in some kind of potential energy field. So this is what you would use to figure out what the orbitals of electrons in an atom or in a molecule would look like. Okay, so this is important, of course, in chemistry. And there it is, the Laplacian. Again, you have derivative with respect to time, and it's going to be pushed around by the what the Laplacian of this function is. Psi here is the wave function of the electron or whatever particle. Suffice it to say, the Laplacian is one of the most important second derivative notions in these kinds of subjects in chemistry, physics, engineering, these sorts of things. Okay, and there's much more that that could be said about this. There's many more other kinds of equations like this. All right, this is called the scalar Laplacian. There's something called the vector Laplacian. The vector Laplacian, so you take a vector field and you take you basically take the Laplacian of this vector field. It's just you take the Laplacian of each of the components separately. Okay. And this is not quite as common as the scalar Laplacian, but it does show up in things like electromagnetism. So the electric field, magnetic field, when you want to describe waves in the electromagnetic field, this comes up. Okay, so this gives rise to notions like light and radio waves and things like that. It is curious, by the way, that the vector Laplacian is given by this formula. I mentioned earlier that, okay, so this one's the scalar Laplacian. I mentioned earlier that these two things existed. It's if I take their difference, it turns out you get the vector Laplacian. And here we go. Here's the chart again. I put in the scalar Laplacian here. These, I put question marks, but I subtract them, and now we get this vector Laplacian. These guys, for whatever reason, are not quite as common. They don't come. They don't have a name that's attached to them or anything like that. Okay. All right, so there we go. Those are the different ways of combining these guys into second derivatives. Okay. Sometimes you get zero, sometimes you get a scalar Laplacian or a vector Laplacian. This one, these two are maybe not so remarkable to get their own name. All right, now I'd like to talk about different ways of seeing Green's theorem. Okay, now here's Green's theorem again, and you'll notice now that okay, of course, this one, as I said, was just f dot dr, and now you'll notice that this looks a little familiar because it, well, for several reasons. We've been looking at it for a while, but it also shows up in the formula for curl. Now, here's the thing. This is a two-dimensional problem. P and Q are two components of a two-dimensional vector field, right? Curl happens only in 3 dimensions. But I can make this 3-dimensional. What I do is I take P and Q and put 0 as my third component. And of course, P and Q don't depend on Z. They didn't depend on Z before. They're not going to depend on Z now because P and Q came from a two-dimensional problem. And if you have that situation, then curl of F is going to look like this. We know that this is the Z component of the curl, Q sub X minus P sub Y. These two are going to be 0. The reason is these two do not depend on Z, and this R is equal to 0. If you look in the formula for curl, what you have are partial derivatives of P with respect to Z, partial derivative of Q with respect to Z, and various partial derivatives of R. And all of those are going to be 0 because P does not depend on Z, Q does not depend on Z, and this one is 0. So those are going to be 0. Curl of S is going to look like this. And then I can just say, okay, just take this component of the curl. I can say dot it with K, and then I'm going to get that. And so this, of course, is integral of F dot dr. This can be written as curl of F dotted with K. And so this is a way of writing it if I just want to write things using vector fields like this instead of breaking it up into P and Q. So that's kind of cool. By the way, this does have some kind of meaning, right? When I'm traveling around, remember if you are traveling around, let's say, a lake on a bike, and you may feel the wind is always at your face or something, so that this is negative. Okay, if F is the wind velocity. Okay, what it says is on the lake itself, if you add up all the little curls everywhere, there's got to be some curl that's negative that's producing this. In other words, the total amount that you feel that the wind is against you is distributed somehow throughout the whole lake. Okay, so as you go around this lake, right, you're going to get wind against you. It must be that there's swirling of wind somewhere around in the middle. Okay. All right. There's another form of Green's theorem. Let me show you that. Okay, so here's Green's theorem. Here's what I'm going to do. I'm going to replace P with negative Q and Q with P. Okay, so this is going to be negative Q, that's going to be P. And P and Q are just functions, right? It doesn't matter what I call them, right? So I'll just call this negative Q and I'll call this one P. Call this one negative, sorry, call this one P and call this negative Q. And what that does is this makes this P sub X and this makes this Q sub Y with a plus sign now. This also changes this around, but this is kind of nice because this is a divergence, a two-dimensional divergence. Okay. And over here, we have something weird. Let's look at that. I can rewrite that as P comma Q dotted with dy comma negative dx. So this is dy compares with P, and negative dx pairs with Q, like this. So in other words, this is F, and like I said, this is the divergence of F. So the question is, what is this thing? We know dx, dy, that's dr vector. What is this thing? Well, if this is dr, you'll notice this dotted with that is equal to 0. So dx times dy, dy times negative dx, add it together, you get 0. That is to say that these are orthogonal to each other. So if this is dx, dy, and this is dr, okay? Now, this here is what you get when I take for my x component dy. So x component is dy, and the y component is negative dx. That is going the opposite way like this. And the point is these two vectors are orthogonal. This one is the dr vector. This is the vector that I want. Okay, dy comma negative dx. Now dr is of length ds, so this will also be of length ds. R points in the direction of t. This is going to point in the direction that's perpendicular to t. T, remember, is the unit tangent vector, the thing that points tangent to the curve. This is going to be pointing perpendicular to that. And if I draw this diagram here, you'll see that as you go around, n is this vector that points perpendicular to t, is exactly what we need here. I should mention that you're used to n, capital N, and I've written lowercase n here. Capital N is different from lowercase n. So capital N points perpendicular to t, but which way it goes depends on which way the whole thing curves. So capital N is going to point inward here because that's the direction that the curve is bending. On this part here, though, capital N is going to be pointing out the same direction as lowercase n. So capital N and lowercase n are sometimes the same, sometimes opposite, depending on which way the curve bends. Out here, it's opposite. On places like this, it's pointing the same way. Lowercase n is always pointing outward. Okay, it's always pointing outward. That's what this is. Okay, so there you go. dx dy, that's dr, which I write as t ds. This thing is n ds. So I can rewrite our second form of Green's theorem like this. Integral of f dot n ds is equal to the double integral of div f dA. That's this second form here. Written like that. All right, there's a way to understand this. So remember what divergence means, right? And so imagine your regions broken up into little squares, and in each square, I'm trying to add up all the ways in which things are moved. So imagine people are moving, right? And div of f is just saying to what extent people are leaving this little region here. Okay, and there's div of f at this region as well. And if I add them all up, you'll notice that people going from here to here, people going from here to here cancel. Okay, so when I take the div of this plus the div of that, I'm talking about how many people are leaving this altogether. Right, so people going from here to here, people going from here to here, that is not going to affect the total amount of people in this region here. And if I just do this with all of the different points here, then all the things internally, these are people like moving from one state to another, is not going to be counted. All that's counting is how many people are leaving altogether. And so you see that the integral of div of f over everything is just, you look on the boundary, okay, and ask how many people are leaving at each of these places along the boundary. So there we go. These are the different forms of Green's theorem. This is the original form you wrote down. We can write it in vector form like this. Okay, I've written it as f dot dr, but actually I've written it as f dot t ds. That's the same thing. I did that to make it an analogy to this one. This first one, if I just switch around p and q and put a minus sign on one of them, I get this one, which in vector form is this. Now this becomes div, this becomes f dot n ds. So these are the various forms of Green's theorem. I like the forms that have the vectors in them because that I can actually put an interpretation behind. Whereas when I have p's and q's, it's maybe a little less intuitive as to what this is talking about. All right, the third thing that the last thing I wanted to mention. I've talked about all the three things I was going to talk about. Next thing I wanted to mention is what we're going to do next time. So in class on Monday, we're going to do surface integrals. So note I've covered 13.5, so everything that is in your homework has been covered. The homework's due on Monday when you get back. Surface integrals are the next thing on the topic. Okay, so just like we had line integrals, we're going to have surface integrals. So just like we had a line integral talks about integrals that are based on a curve, which we parameterize. Similarly, surface integrals, okay, we're going to have a surface in 3 dimensions, and we're going to find the integrals on that. And they're going to be two kinds, this kind and that kind. This one is a scalar function, okay, a regular function, and I'm going to integrate it on ds. This is a capital S here. Okay. And this capital S, I guess, also stands for surface, but this could change, right? I could call this A or something. That's if I call this surface A. This one is always going to be D capital S. This means surface area. So this is just like a double integral, except instead of on the plane, this is going to be on the surface in 3 dimensions. This is a similar sort of thing, but we've got a vector field here, and dotted with, I haven't said what this is, but it's a vector version of area. And so we're going to have to interpret what that means. But it's basically, if you understand line integrals, the basic understanding of this is the same. You're going to break up your surface into bits, multiplying this times this little bit of area. Okay? And the way we compute this is the same way we compute line integrals. That is, in line integrals, we don't compute things on the curve. We compute things back with t, with the parameterization. The same is true for this. We're not going to compute things on the surface. We're going to compute things using a parameterization. So you should review line integrals because, of course, this is going to be sort of the next version up of line integrals, surface integrals. Also remind yourself about parametric surfaces and how to parameterize these things. All the problems that you are going to work are going to involve parametric surfaces, and so you should remember how to parameterize everything that we discussed. Surface area. Actually, when we did the section on surface area, is our first glimpse as to how we're going to approach surface integrals. Remember, we don't calculate surface area on the surface itself. We do a parameterization, and that's exactly how we're going to do this. So you might want to look back at that. The formula is going to involve an extra factor, and that's change of coordinates is a good chapter to review to understand how that goes. Cross product is going to be important because it has to do with the area of regions. Well, in surface area, you saw that. So in other words, surface integrals, when we talk about surface integrals, we're going to tie together quite a lot of this course, and the whole thing kind of culminates in versions of Green's theorem that have to do with surface integrals. Green's theorem is going to generalize when you get to, it's going to generalize 2 ways actually. This version generalizes to what's called Stokes' theorem. This one generalizes in 3 dimensions to what's called the divergence theorem. Okay. I will put together a little video to review for the midterm. I figured that that might be a good way to do this. I'll probably put that out like Friday or Saturday whenever I finish it. This is the sort of thing I might say. Remember when we review for midterms, I talk for a while about things and then I open it up for questions. And so, of course, I can't open it up for questions in this format, but I can. Just do the first part, just run over all the material we've covered up to now. All right, so this is the more or less the end of our time doing these video lectures, with the exception of my giving the review for the midterm. So I'll see you for that one, and then I'll see you on Monday when you come back to campus.